Good afternoon. I am Dr. Jaganmohan Jannalagada. So, we are going to study the course titled Advanced Statistical Methods. The course number is Ba Zg524. So, this course may be an extension of the basic course titled Probability and Statistics. So, in Probability and Statistics course, you might have studied the basic concepts of probability as well as the basic concepts of statistics. In this course, we will extend this course and study the advanced statistical methods. So, as per the course handout of this course, first we start the basic statistical methods which we have already discussed. Based on those, we will study some advanced statistical methods. So, if you see the course handout, so we are following the prescribed textbook for the first unit. So, we are starting with chapter 7 of the prescribed textbook. So, chapter 7 of our prescribed textbook deals with sampling and sampling distributions. So we know the concept of sampling and sampling distributions, but still the first two lectures of our course will deal with chapter 7 sampling and sampling distribution, chapter 8 interval estimation, and chapter 9 testing of hypothesis. Yeah, I will read the basic course handout and all those things in a moment. So, if you go through the course handout, so we have totally 3 prescribed textbooks. So, textbook 1 is Statistics for Business and Economics by Anderson, Sweeney, Williams, Cam, and Cochrane. So, it is a 12th edition book by Cengage Learning. And the textbook T2 is Deepak Chawla, Neenu Sodhi, Research Methodology, Vikas Publications, 2012. And textbook 3 is again by Anderson, Sweeney, Williams, Cam, and Martin. The book titled Quantitative Methods for Business. Again, it's a 12th edition, Cengage Learning for 2013. So these are the 3 textbooks which we are going to follow in our course, of which initially we are starting with the first textbook. Yeah, so if you want, we can buy these 3 books, but anyhow we will solve rigorously as many as problems from each textbook, and most of the concepts of the textbook I am providing through slides. So apart from this, one can buy the textbooks and go through the concepts. But as much as possible, I am just providing the information from the textbook on slides, and also as many as problems I'll do from the textbook. Even I'll mention the exercise number and also problem number on each slide. So at present, we are starting with textbook 1. So whenever I'll change the textbook to 2, I'll inform. So first of all, I'll start with textbook 1 for the basic things and some advanced topics. So if you go through our course handout properly, then we have a wide variety of advanced statistical methods we are covering. Like we'll start with sampling, then estimation, after that testing of hypothesis, after that ANOVA, regression, and non-parametric tests. So we'll start with the basics of our course. Of course, these are the advanced topics of the previous course. So we'll start with uh, chapter 7, 8 and 9 of textbook 1. First of all, we study all those topics as basics for our course. They include what is sampling, what is estimation, and what are the basic things of testing of hypothesis. So anyhow, I'll keep on intimating which chapter of which textbook I'm preferring, which problems of which textbook I'm solving. I'll intimate you every time. So we'll start with the basics of our course today. So I'm referring textbook 1 of our course handout for this chapter 7. So the chapter 7 of textbook 1 titled with sampling and sampling distribution. So what are the contents which we are going to study in this chapter are selecting a sample, point estimation, introduction to sampling distributions, sampling distributions of X bar, that is sample mean, sampling distribution of P bar, that is sample proportion, properties of point estimators, and other sampling methods. These are the contents which we are going to study in chapter 7 of textbook 1. Yeah, let's start with concepts of sample, parameters, and statistics. Then we'll move to point estimation and then finally interval estimation. So start with the concepts of population. So you know very well a population is the set of all objects under study. So whatever the objects which we are going to study, that collection can be taken as a population. And you know very well that it is difficult to study the characteristics of population at a time. That's why we will take a small sample subset of the population known as sample. So a sample is a subset of the population. And you know very well that for a given population, one are very much interested to calculate maybe population mean, population standard deviation, population proportion, and so on. So what are those numerical characteristics which we are going to calculate for a population are known as population parameters. So our interest is to calculate them. But population is very large and it is difficult to calculate them. That's why we will take the help of a sample. So that's why the process of drawing a sample from a population is known as sampling. So what is the primary purpose of sampling is because the population is very big, it is very difficult to calculate parameters. So we calculate the same for sample and we estimate the population parameters through these values calculated for sample. And also we will test the hypothesis about population parameters based on the information of the sample. Please remember that if we use a proper sampling method, then only the values which we are calculating for a sample will provide a best estimate for a given population parameter. So immediately one can ask a question like, we are talking about ideal statistical method to draw a sample. So one can ask us like how to draw a sample and what are the available methods and concepts. So you can select a sample always either from a finite population or an infinite population. These two generally come into the picture. So for sampling from a finite population, the best method of drawing samples is simple random sample. So what do you mean by a simple random sample? So suppose there is a population of size capital N and I want to draw a sample of small n. Then simple random sampling means Each unit of the population has an equal chance of being included in the sample. This is known as simple random sampling. So I'll repeat that. If you want to draw a sample of size small n from a finite population of size capital N, then every unit of the population has an equal chance of being included in the sample. Sorry, this is known as sampling from a finite population. So in sampling from a finite population, you can have two more concepts to study. One is sampling with replacement, the other is sampling without replacement. So the name itself says that sampling with replacement means, like, suppose if you want to take an item, so you will take an item from the population, you will check it, and again you will replace in the population. Yes. So obviously what happened, the next item which we are going to take from the population is independent of the previous one. Am I right? Yes or no? Is it correct? Yeah. And the second one is sampling without replacement. What do you mean by sampling without replacement? In sampling without replacement, first you will select an item, you will check it, and you will keep it aside. And again you will take one more item from the sample. So here what happened, the second item is depending upon the first item. So that's why here the selections are not independent. So I'll repeat one more time, sampling with replacement. Like for example, there is a bunch of maybe a lot of 100 bolts or 1000 bolts, and you want to pick a defective bolt. So the process is like, maybe first you will take a bolt from the pack of bolts. First you will check whether it is defective or not. Then what happened? Again you will put it back into the lot. So which means that if you want to take a second chance, second trial, then it is always independent of the previous one because you have already replaced it. Whereas in without replacement, what we are doing that, like for example, I'll give an example like, I want to pick the bolts until I get a defective bolt. This is what the question I'm giving. I want to select the bolts until I get a first defective bolt. So what you will do, first you will take a bolt, you will check it whether it is defective or not. You will not keep it inside, you will keep it aside, and you will take the second bolt from the lot. So what happened? Obviously, the second bolt which we are taking from the lot is always depending upon the previous one what you have selected. This is without replacement. So simple logic. If you are replacing the item what we have got in the sample is known as with replacement, and the second one is without replacement. And I'll ask you a simple question. Suppose if we are using a sampling technique with replacement, are the draws which we are drawing independent or not? Independent or not? Of course, right? Independent or not? Yes, they are independent. But whereas in without replacement, they are of course dependent. But if the population is very large, maybe you can have some adjustments that we will see in the coming lectures. Now we'll move to the next one. Yeah, the question is that it is depending upon the situation what we use. Sometimes without replacement is good if there is a very like a finite population and you keep on checking for defectives. That's what. So it depends upon the situation what we use. I'll give you an enough number of examples to easily identify. Now the next one is sampling from an infinite population. So if the population is infinite, obviously there will be a problem of drawing, but still you have to assume that each item of the population has an equal chance of being included in the sample and each element should be selected independently. Yes, sir. That's what we have but clearly we will show you the applications of infinite sampling. Yes, sir. Now, we'll come to the important concept called estimation. So, I'll repeat one more time. The interesting part of sampling is that if the population is very big and it is difficult to calculate their characteristics known as parameters, we will take a small sample from the characteristic using which you will approximate your population parameter. This process is known as what? Estimation. So I'll repeat what is an estimation. Suppose there is a big population, you want to calculate its numerical characteristics known as parameters. Since the population is very big, it is difficult to calculate them. Instead of that, you will draw a small sample from the population. You will calculate the same characteristic for the sample and using which you will approximate your population parameter. This is known as what? Estimation. And the sample characteristic which we are used to estimate the population parameter is known as estimator, and the value is known as estimate. I'll repeat, estimation is the process of approximating population parameter by a sample characteristic known as sample statistic. Estimator means the sample statistic, and estimate is any particular value of a sample statistic is known as estimate. Should understand the difference between three words: estimation, estimator, and estimate. Right. Now, if you are estimating this population parameters point to point, then like we are giving the point to point value, it is known as a point estimation. So point estimation is a form of statistical inference. So characteristics of a sample such as sample mean, sample standard deviation, sample proportion, they are called statistics. Whereas the same calculated for population are called parameters. So we use statistics to estimate parameters. So statistics are known as estimators. Like for example, if you want to estimate population mean, we use sample mean as an estimator. If you want to estimate population standard deviation, we use sample standard deviation as an estimator. If you want to estimate population proportion P, we use sample proportion P bar as an estimator. Yeah. There is an interesting point to understand that what is the difference between a target population and a sampled population. The target population is the population we want to make inferences about, and the sampled population is the population from which the sample is actually taken, the feasible one. Most of the cases we have to make the target population and the sampled population is as close as enough so that you will have an accurate result. Now, I'll come to a point here. So first of all, I want to repeat one more thing that we want to calculate population parameters. They are simply numbers for a population. But what happens, we want to estimate them using sample statistics. But sample statistics value varies from sample to sample, right? So if I take a sample 1, I will have a different sample statistic. If somebody takes another sample, it will have a different sample statistic value. So that's why sample statistic value differs from sample to sample. That's why a sample statistic can be treated as a random variable rather than a constant. Yes or no? So sample statistic is not a constant because it depends upon the sample. So if you change the sample, its value may change. That's why population parameter can be taken as a constant, whereas sample statistic is a random variable. It depends upon the sample which we calculate. So that is the reason if you treat a sample statistic as a random variable, you know very well that for every random variable you can calculate a sampling distribution or simply probability distribution. So I'll tell you that the probability distribution of a random variable or random variable is here statistic known as sampling distribution of the statistic. So what do you mean by a sampling distribution of statistic? The sampling distribution of a statistic is nothing but the probability distribution of the statistic because statistic is a random variable. Now, one of the prominent statistics are sample mean x bar. So now we want to concentrate on how to construct the probability distribution of the random variable x bar, simply the sampling distribution of x bar. So the process is, suppose if you take the first circle or oval in the slide, we want to calculate the population mean mu, but we don't know. That's why what we will do, we will take a simple random sample of n elements from the population. That is a sample of size n. Now for that sample of size n, we will calculate the sample mean x bar. And that x bar is used to approximate our mu. This is the process of estimating population mean mu by sample mean x bar. But in this process, you are drawing a sample of size n, but that sample varies from person to person. That's why x bar cannot be treated as a simple constant. It can be treated as a random variable. So different samples produce different x bars. That's what the concept. Now, now we want to calculate the probability distribution of x bar or simply sampling distribution of x bar. You know very well for every probability distribution we need its mean, known as the expectation of probability distribution of x bar. That is known as expectation of sampling distribution of x bar. Please remember x bar is a random variable. So if you calculate, it comes out to be mu. That is a surprising thing. So that's why the expectation of sampling distribution of the random variable x bar is mu. Now we want to calculate the variance or standard deviation of the random variable x bar. So we have two formulas for finite population. The standard deviation of the random variable x bar comes out to be square root over n minus n by n minus 1 into sigma by root n. Whereas for infinite population it is sigma by root n. Please remember I am using the rotation sigma subscript x bar to denote the standard deviation of the random variable x bar. So if you take the formula square root over n minus n by n minus 1, it is known as what? Finite population correction factor. Right? Then one can ask you that how do you determine a population is finite or infinite, any numerical measure. So you see that a finite population is treated as infinite if small n by capital N is less than or equal to 0.05, uniformly accepted measure. N is small n is sample size, capital N is population size. Please remember, sometimes this standard deviation of x bar is also called a standard error of x bar. These things you have studied already. So this is what the sampling distribution of x bar. Now we will talk about the sampling distribution of x bar's known probability distribution. So there is an interesting observation that if the population is following normal distribution, then the sampling distribution of the random variable x bar also follows normal distribution. But there are some more interesting observations, like if the sample size is 30 or more, if the sample size is 30 or more, then the sampling distribution of x bar is always approximated by a normal distribution. Is it right? Have you understood? That if a sample size is large, generally large means we are taking 30 or more. But there is a very interesting theorem called central limit theorem. Do you know that? So what do you mean by central limit theorem? The previous slide says that if population is normal, irrespective of sample size, sampling distribution of x bar follows normal distribution. But if the population is not normal, then central limit theorem says that the sampling distribution of x bar follows normal distribution if the sample size is very large. So please understand the difference between the current slide and the previous slide. The current slide says that if the population is any distribution following, but the sample size is very large, then the sampling distribution of x bar follows normal. The previous slide says that, if the previous slide says that if the population is normal, irrespective of sample size, the sampling distribution of the random variable x bar follows normal distribution. I'll repeat. If the population is normal, irrespective of sample size, the sampling distribution of the random variable x bar follows normal. Whereas central limit theorem says that if the population is following any distribution and the sample size is large, then sampling distribution of x bar follows normal distribution. So this is a very interesting observation you should remember. Any queries on these two slides? I'll take a small break for a minute and I'll come back. Please think once. So, just now we have observed that the importance of central limit theorem. Now we will talk about the next random variable or the next sample statistic P bar. So that is sampling distribution of P bar. So the concept is like there is a big population and you want to calculate the proportion of some characteristic. So the proportion is denoted by small p. Now what we will do is that from that big population, I will find a small sample of size n from that. For that sample, I will calculate the proportion known as sample proportion P bar. This is the sample statistic. So then this value of P bar is used to make inferences about the value of P. I'll repeat the central limit theorem in a while. So now we are calculating the sampling distribution of the test statistic or the random variable P bar. So the concept is there is a big population for which I want to calculate maybe the proportion of a particular concept. Like for example, there is a huge collection of bolts. I want to calculate the proportion of defective bolts. that is my population proportion P. So though the collection is very big, it is difficult to count the number of defectives. For that reason, for that reason, for that reason, I will take a small sample of size n, and for that sample, I'll calculate the proportion of defective bolts. This is known as the sample proportion or simply the test statistic. And using this sample proportion P bar, I will make an inference about my population proportion P or the proportion of defective bolts in the big collection. So this is what the concept of sampling distribution of P bar. But please remember that here, yeah. So please remember that this sample may vary from person to person. That's why sample proportion may vary from person to person. So it is not a constant. It is a random variable. Depends upon the sample which we have calculated. So that is the reason the test statistic here, the sample proportion is a random variable. For that, I am calculating the probability distribution. So probability distribution of P bar, the sample proportion, the test statistic is known as what? Sampling distribution of P bar. So for every probability distribution, or we are calling as sampling distribution, or we are calling as sampling distribution, for that, we need to calculate expectation and variance. So first I am starting with expectation. So the expectation of the random variable P bar is simply equal to small p, that is the population proportion. This is what somewhat surprising for us. And I'm calculating the variance or the standard deviation of the random variable P bar, the test statistic. So for finite population, the standard deviation of P bar is square root over n minus n by n minus 1 into square root over P into 1 minus P by n. This derivation you might have done in your DropStat course. Whereas for an infinite population, sigma P bar, I'm using this notation because I'm calculating the standard deviation sigma for the random variable P bar. So which is equal to square root over P into 1 minus P by n. Please observe that in finite population there is an extra term square root over n minus n by n minus 1. This is known as finite population correction factor. When finite population becomes infinite, this square root term becomes 1. That's it. That's why you got the infinite population formula. I'll show you that. So then one can ask you in the proportions case, what is a large population, what is a small population. So that's why I'm writing here, the sampling distribution of P bar can be approximated by a normal distribution when the sample size is large enough. So when can we say that a sample size is large enough if n into P is greater than or equal to 5 and n into 1 minus P greater than or equal to 5. Then we can approximate the sampling distribution of P bar by normal distribution. So anyhow, I'll revise these two distributions one more time. So I'll repeat one more time the sampling distribution of X bar as well as sampling distribution of P bar. So please remember that. So if this is a big population, This is my population. For population, I am concentrating on a particular parameter as population mean. Though the population is very large, I cannot calculate mu. That's why I'll take the help of a small sample. For this sample, I'll calculate sample mean. It is denoted by x bar. So using this x bar, I'm going to approximate mu. But the surprising thing is that different samples may produce different x bars. So that is the reason the sample mean x bar, simply I'm calling as sample statistic, is not a constant. It is a random variable. It varies from sample to sample. That's why sample statistic is not a constant in general. It is a random variable. So if you change the sample, the value of the random variable changes. So that's why for a particular sample, only you will have a value for sample statistic. In this case, it is sample mean. Now, what I want to explain you that once you came to know that the sample statistic is not a constant, it is a random variable and it varies from sample to sample, then the basic concepts comes into the picture. You know very well that for a given random variable, one can construct the probability distribution, one can calculate expectation, one can calculate variance, one can calculate standard deviation. These type of concepts are known as what? Probability distribution of a random variable. Now here our random variable is a sample statistic, that is x bar. Then you can calculate the probability distribution of x bar. So that is known as what? Sampling distribution of x bar. So once you know the sampling distribution of x bar, obviously you can calculate the expectation of your random variable x bar, variance of your random variable x bar, standard deviation of your random variable x bar. So that's what we have. So the expectation of random variable x bar is mu, and the standard deviation of the random variable x bar is given by two different formulas, one for finite population and the other for infinite population. You please think that a finite population can be treated as infinite by the universal measure small n by capital N is less than or equal to 0.05, which means that if small n by capital N is very small, the term square root over n minus n by n minus 1, we are calling as a finite population correction factor, becomes 1 and the formulas becomes identical, right? And sometimes the standard deviation of x bar is also known as the standard error of x bar. Yes. Now coming to the picture, what type of distribution your random variable x bar follows? Because you know these concepts already, one can say that if your population is normal, then the random variable x bar also follows normal distribution. But if your population's distribution is unknown, like it may be normal or it may not be normal, then if you take a large sample size, in such a case, x bar follows normal distribution. This is the central limit theorem. So now tell me, do you have any queries in these two concepts? Yeah? Any queries regarding central limit theorem? Clear, thanks. Yeah. Now, similarly, the same logic can be applied to a different sample statistic, that is population proportion, sample proportion. Population proportion is your parameter. Sample proportion is your statistic. But statistic cannot be a constant. It is a random variable because different samples produce different statistic values. That's why here our P bar, our sample statistic, our sample proportion becomes a random variable. So for the random variable P bar, I want to calculate the probability distribution. That is known as sampling distribution of P bar, right? So once you know the probability distribution of P bar, easily to calculate expectation of P bar, the random variable, variance and standard deviation of the random variable P bar. So that also we did. Correct. Now, what distribution your P bar follows? That is an interesting question. So, if your population is large enough, like the condition is n into, sorry, if your sample size is large enough, the condition is small n into small p greater than or equal to 5 and small n into small q, that is 1 minus p greater than or equal to 5, then you can treat your sample as large, and in such a case your P bar follows normal distribution. So any queries regarding these two concepts? Any queries? Any questions? Yeah. So I can go further. Yeah. Can I go further? Any queries in these two? Sampling distribution of mean, sampling distribution of proportion? Yes. Thanks. Now, before going to the next concept, I am just closing with simple points like what type of properties an estimator, a point estimator should have. There may be many properties, but yeah, actually the examples I have kept aside. Once I complete the theory, I'll start doing problems from this article. That's the way I'm just doing. So I'm about to complete the 7th chapter in a while. Then I'll start a couple of questions on this thing. So now the next one is, sure. The question is like we have done only simply two important sampling distributions, and the current slide which I'm going to teach is only a simple theory. So that's why I'm just delaying for a 5 minutes. That's it. Maybe after the next immediately I'll start the problem. So the question is like, just now you have understood the concept of point estimation. So you know point estimation means there is a big population. A population has a particular characteristic. For example, population mean you want to calculate. Though the population is very big, so it is difficult to calculate. For that reason, you are taking a small sample. For that sample, you are calculating the same characteristic. So for population, if you are talking about population mean, so then for sample, you will calculate the sample mean. The population mean is the parameter, the sample mean is the statistic. So finally, what we are doing, we are estimating population mean through this sample mean. So this is the process of point estimation. Yes, and the sample mean is known as estimator. And for a particular sample, the value of the sample mean is known as estimate. But please remember that population parameter is always a constant which we are interested to calculate. But the sample statistic which you are going to calculate for a sample need not be a constant. It is a random variable, varies from sample to sample. That's why sample statistic is a random variable, depends upon the sample what we take. Now tell me, I'll ask you a few questions. Before that, I tell you that the sample statistic is known as an estimator, probably point estimator. what properties a point estimator should have so that it can be called as an ideal one, and it removes the ambiguities and errors, and it gives a close, very close value of the parameter. There may be many in the literature, but most probably the important one are unbiasedness, efficiency, and consistency. So, what is unbiasedness, what is efficiency, and what is consistency? So, unbiasedness means expectation of the estimator should be equal to the population parameter. Simply, expectation of the statistic is equal to the population parameter. For example, if you take means, expectation of sample mean is equal to population mean, then we say that X bar is an unbiased estimator of mu. The next one is efficiency. Like suppose for a given population parameter, there may be many point estimators. For example, if you want to estimate your population mean, not only sample mean, sample median, sample mode, so on and so forth, many can be used to approximate your population mean. So that's why for a population mean, you can have many unbiased estimators, of which estimator has a minimum standard deviation that is said to be the efficient one. Yeah, I'll come to that point. I'll repeat once. The question of efficiency is, for example, if you want to estimate population mean, for estimating population mean, you can have many unbiased estimators. For example, sample mean is an unbiased one, sample mode is an unbiased one, sample median may be unbiased one. But for a given population parameter, there may be many unbiased estimators, of which one unbiased estimator will have smallest variance or smallest standard deviation. That unbiased estimator is known as efficient. I'll give you the examples. I'll come to that. The last one is consistency. So a point estimator is consistent if the values of the point estimator is very much close to the parameter when the sample size is very large. As n goes to infinity, the sample size goes to infinity, the difference between the sample statistic and population parameter will be very zero. Yeah. I'll stop here and I'll come in a minute.